So welcome to lecture number 12. So today we will speak about output analysis. It's a new chapter. So we will speak about confidence bands for our Monte Carlo estimator, the numerical evaluation of the convergence rate of a Monte Carlo estimator, and we also go back to the beginning of our lecture, namely to quantify or to validate the quality of our pseudo-random numbers. So the first topic of today's lecture is Monte Carlo and confidence bands, as I said, and here's our setup. As almost always, we are given a real-valued random variable z with finite second moment, and we want to compute its expectation. So theta is unknown, and theta is the expectation of z. And the classical Monte Carlo estimator is like this, as always. So zi are IID copies of z, and then we sum up and average. And also all our variance reduction methods will fit in this framework because, well, variance reduction is not to take the initial z, but to take a different z. Okay, so that's the setup, our standard Monte Carlo estimator. As I said, we can fit in the variance reduction methods also by using a different z. And let's summarize at the beginning some properties of it. So first, our estimator is bias free, so on average our estimator yields theta. And we also have almost sure convergence through the strong law of large numbers. So for almost all omega in our sample space, we know that the realization of our estimator for n going to infinity converges to theta. Bias-free, almost true convergence. The next property, well, it's a mean square error. We already computed this many times. There's a mean square error, so the squared distance and then the expectation, behaves like 1 over n times the variance of z. So if we take the square root here, we have convergence order 1/2, and the constant is the square root of the variance of z. Okay. But we have more, so we can write down a central limit theorem for our Monte Carlo estimator. So here we now assume that the force moment of our z, well, is finite, so it's less than infinity, and is also greater than 0. Otherwise, we would have a constant variable, and for constant variables, well, the estimator is always good, and here for this problem, we couldn't write down a central limit theorem. Okay, and here, well, is a quantity we always computed in our simulations, or we computed the corresponding quantity if you plug in the realizations of the random variables. So that's the empirical variance, s square n, it's 1 divided by n minus 1, and here we sum up zi minus our estimator squared. That's the well, empirical standard deviation, written in terms of random variables. And then one can show that this quantity converges almost surely to the variance. And even more, so if I look at my estimator, standardize it with subtracting theta, dividing by Sn, and then multiplying with the square root of n, well, then this converges in distribution to a standard normal random variable. Well, so we have a central limit theorem for our Monte Carlo estimator, and this can be used to write down approximate confidence bands for our Monte Carlo estimator. Okay, and here, well, the empirical variance, as I said, we always computed this in our simulations by computing STD, the standard deviation, the MATLAB command for standard deviation. Okay, now let's prove this, and the proof is not really involved, well, if one has enough tools. So by assumption, zi square, they are all IID and square integrable. Why they are square integrable? Well, because we assume that we have force moments, and 2 times 2 is 4. Okay. So on zi and zi squared, we can always apply the strong law of large numbers. So if you look in this line here and replace 1 divided by n minus 1 with 1 over n, well, then we have here the strong law of large numbers. So this average would converge or converges to the expectation. And also here, if we don't have 1 divided by n minus 1, but 1 divided by n, here zi squared, by the strong law of large numbers, this converges to this, the second moment of z, and always p almost surely. Okay, now we don't have 1 over n, but 1 divided by n minus 1. But that's not a problem. N divided by n minus 1 converges to 1. And so we can replace here 1 divided by n by 1 divided by n minus 1 here, and the almost sure convergence still holds. Okay, so we have these two almost sure convergence. We want to say something about this quantity here. And here we have a square, and the first thing one can do is to multiply the square out. If one does this, one gets this expression here. So here we have the zi squared summed up, divided by n minus 1. Here we have 2 times the standard times our estimator, and here we have 1 divided by n minus 1, and here's the sum of the zi's. And for the last term we get the estimator squared times n, because there's a sum, and then divided by n minus 1. Okay, so by our preparations, this converges here to the second moment of z. So this converges to this. Here, this thing converges to zeta squared due to the almost sure convergence of our estimators, and n divided by n minus 1 converges to 1. So we have here, for this term, we have a plus zeta squared. Here, but here in the end we have a minus zeta squared. Where does the minus zeta squared come from? Well, from this part. Because we know this converges here to zeta by our preparation. Our estimator converges to zeta. So this thing here converges to minus 2 zeta squared, and minus 2 zeta squared plus zeta squared is minus zeta squared. So overall, Sn squared converges almost surely to the variance of z. Okay. This was part 1, this convergence, and now we have the central limit theorem here. What can we do here? Well, we have the standard central limit theorem, because, well, zi is IID square integrable, so the central limit theorem, a bit rewritten, is this statement here. The estimator minus zeta divided by the standard deviation of z, which is sigma, the variance of z, times square root of n. Well, this converges in distribution to a standard normal distribution. Okay, now we don't have here sigma, which is the standard deviation of z, but we have Sn. But we know Sn squared converges to the variance, so Sn converges to the standard deviation. So we have here, if we don't have sigma but Sn, okay, we at least know that sigma n converges to sigma. And then we can use Slutsky's lemma, which says if we replace this thing here by something which converges almost surely to sigma, then the convergence in law is still true. And this finishes the part, well, this finishes the second part of the proof. Okay. So what is this good for? We have this convergence in law. Well, we have this convergence in law here, and because we have convergence in law to a standard normal distribution, we can say this thing here about the probabilities. If we look at the probability that our standardized estimator is an AB, well, and if we let n go to infinity, then we know that in the limit this probability is phi b minus phi a, and phi is a distribution function of the standard normal distribution, and a has to be less than b to make sense. So in the limit, this probability here is given by probabilities of the standard normal distribution. So if n is sufficiently large, well, in an approximation we can drop the limit and replace the equality sign by an approximation sign. So this probability here is approximately phi b minus phi a. Okay, so what is this good for? We don't know theta, but we can rearrange it, because we are computing our estimator, and we can compute this standard deviation. So rearranging, so rewriting this relation here, gives the following inequality. So the probability that theta is greater than the standard estimator minus b times Sn divided by square root of n, greater than theta is greater than this, and less than the standard estimator minus a times Sn divided by square root of n. This is approximately phi b minus phi a. Okay, so we know if we compute our standard estimator, not compute, but the standard estimator minus this expression, and the standard estimator minus this expression here. Well, we know that approximately theta lies in between these two bounds with this probability, and so we can construct confidence bands. So for this we need now to choose A and B cleverly. So in confidence bands you start with a small alpha and choose it small, and you want to have that your estimate lies in your confidence band with probability 1 minus alpha. So we are choosing now A as the inverse distribution function of the standard normal distribution evaluated at alpha half. B is the inverse distribution function of the standard normal distribution evaluated at 1 minus alpha half. Why is this a good choice? Well, if we plug this here in, we get phi of phi inverse, so 1 minus alpha half remains. So we have here 1 minus alpha half. If we plug in the A here, we have phi inverse of alpha half, so we are subtracting a further alpha half, and we are getting 1 minus alpha. Okay, so we have this, and this gives us the following approximate confidence band. Approximate because the probability only holds in the limit, the probability of 1 minus alpha. But this is our approximate confidence band, which we always can compute. So if we look at the estimator minus the inverse distribution function of the standard normal distribution evaluated at minus alpha half times Sn divided by square root of n, and takes the standard estimator plus this bound instead of minus, then we know in the limit our value which we want to estimate lies in this interval with probability 1 minus alpha. Okay, here's one thing I should comment about. So here we have inverse of alpha half. Here we have inverse of 1 minus alpha half. And here we have only the second expression, but with a minus and a plus. So in this case, because we have quantiles of the standard normal distribution, we have the relation A equal to minus B, and we end up with this expression. Okay, so this is the approximate confidence band for our Monte Carlo estimator, and well, this is another reason for computing the standard deviation in our simulations, because the standard deviation gives us an estimate of the variance of z, and it gives us an estimate which we can use to build up these approximate confidence bands. Okay. So here's another one of our running examples of the road system, and here, again, n varies between 10 to the power 2 and 10 to the power 7, and here are the values for the average, which estimates the expectation, and here are the values for this empirical standard deviation, which estimates the real standard deviation. Okay, but now we are computing confidence bands, so we are taking alpha equal to 0.5. So we have to know what is the inverse distribution function of the standard normal distribution at the value 0.975, and this is approximately 1.96. Okay, so we know this value here, we abbreviate it by C, and for our confidence bands we have to compute C times the standard deviation divided by the square root of n, and this quantity here is half the length of our confidence band. And here you can see that with increasing n, while the lengths get smaller and smaller and smaller, and we end up with this expression here, so approximately 10 to the power minus 3. And so if we build for n equal to 10 to the power 7, our confidence band, we have this confidence band here. So approximately the value we want to estimate theta, the unknown expectation, lies between 9.7171 and 971.86 with approximate probability 95%. So that's the confidence band. And well, if you have an application, you should always use the confidence band. Not the 1-point estimate, but the confidence band. That's in the nature of Monte Carlo estimates, well, that they are random, and you shouldn't take the one value for granted or for exact, but you have to build up confidence bands. Okay, so this was the building of confidence bands, approximate confidence bands. And well, in the error analysis, we were always interested in the root mean square error of our estimator. So we have our Monte Carlo estimator Mn, we want to estimate the theta, and we were always interested in this quantity here. So delta Mn, square root of the expectation of the square distance between Mn and theta. This we actually want to know if we want to analyze a Monte Carlo estimator. And well, in the typical calculations, we get that this thing here decays like 1 over the square root of n, and the constant is the square root of the variance of z. So okay, we don't know the variance of z, so this is unknown, and also it's not really clear whether the convergence order 1/2 is only asymptotically, or you can observe already for small values of n. Okay, and so the aim is now to study this expression here by another simulation study, and this leads to the study of the empirical convergence behavior. Well, the first thing is theta is unknown. So in a simulation study of the area behavior, we have to replace theta by a numerical reference solution, theta ref, which is typically computed with very high accuracy and ideally with a different method than Mn. So this is our numerical reference solution. Okay, so we can replace theta by theta ref, but then we have to know this quantity here. And this quantity here, well, the square distance or the expectation of the square distance between Mn and theta ref is also typically unknown. But what we can do is, well, we can approximate this quantity here by another Monte Carlo simulation. So we estimate the expectation by another Monte Carlo simulation. So we are generating copies of our estimator, the MNI, they are IID copies of Mn, while we subtract our numerical solution, the exact numerical solution. It's a contradiction in terms, but you know what I mean. We square it, we sum it up, we average, and then we take the square root. And then we are getting this quantity here. So it's delta Mn with a ref and an amp. So the ref is for the use of the reference solution, and amp is for, well, that we are replacing the expectation by its Monte Carlo estimate. So we are looking at the empirical mean square error. Okay, and well, to do this, you should choose n sufficiently large to have a good approximation of this expectation here. What sufficiently large is, well, that's another thing, but in the simulations you have to find out by hand. Okay, so what is this good for? So if we assume that we have this relation here, so theta mn squared, that's the squared root mean square error or the mean squared error, that this quantity here behaves like a constant times n to the minus alpha. So if we assume this relation, what we can do now is we can estimate the constant c and alpha by a linear regression for this expression here. So what we have done from here to there, well, we have taken the logarithm. So we can take here the logarithm, we get this expression. If we are taking the logarithm to the right, well, the minus alpha goes in front, then we have times log n plus log c. Okay, it's a linear relation for given, if we have given this quantity and this quantity here, and the unknowns are minus alpha and c. So it's a linear equation. And well, next step would be to compute our empirical root mean square error for different values of ni. Well, this is clearly computational intensive, but well, it's a study of the error, and the study of the error can take as long as one likes, because it's not used for the simulation itself, but to say something about the method itself. Okay, so we have now this for different ni's, and so we are getting for different ni's, we are getting different values of our empirical mean square error, with this exact solution replaced by the reference solution. Okay, and well, we have two unknowns, and you should do more than two to take two values of the ni. So typically we have 10 or 12 or 8 or 6, so at least more than two values. Okay, so we have an overdetermined linear system for alpha and log c. But this we can solve using the standard least squares approach, which you have seen in Introduction into Numerics and probably also in Stochastics too. So here we have a system of linear equations which we can solve using the standard least squares approach. Okay, and here's again our running example. So again the road system, and here we estimated, we did standard Monte Carlo and estimated the empirical root mean square error with 10 to the 4 replications for the approximation of the expectation. And for theta we use this theta ref. How did we get it, or how did I get it? Well, I used the Halton and the Sobel estimator. So quasi Monte Carlo has the better convergence rate than Monte Carlo, so this approximation should be more accurate. In addition, I use the antithetic Halton and Sobel estimator. What does antithetic mean here? Well, all the variance reduction methods, you can also do them with quasi Monte Carlo. You only need to replace the random numbers by your low discrepancy points. Well, that's the antithetic versions of the Halton and the Sobel estimator for the expected minimum time to pass from A to B. And I didn't use one of them, I used both and averaged them, and then I got this value. Okay, and here are the values I observed. So it's only a small study, and rise between 10 to the power 2 and 10 to the power 5, so at least 4 values. And here we have the following values for the empirical mean squared error. And this already behaves wonderfully. Why wonderfully? Because the constant in front, this estimate for the C, well, it's 1.5 something, so here's not a big change. And also, if we increase here the number of the replications, so the small n, by 10, well, we get a decay here in the error by 1 over 10 always. So this is a very nicely behaved example. And so convergence order 1/2 should be fine. So 1/2 instead of 1, because we have here the square root. And also the estimate for the constant is also 1.5 something. Okay. But you can do a regression estimator, and then one gets the following values here. The following values, so alpha hat is 1.001.6, so if you divide this by 2, you have approximately 1/2, or a very good approximation of 1/2, and this is the estimate for log C. Okay. Okay, now let's start with the last section of today's lecture, statistical tests. So here we go back to the beginning of our lecture, lecture 2, long before Corona times. And while statistical tests are methods for validating the quality of our pseudo-random numbers. And we have already seen an empirical test, namely the CAT test. Well, this was used to check whether our pseudo-random numbers are imitating nicely the uniform distribution on 0, 1. Further tests one can do and should do, namely independence tests and goodness of fit tests. So independence, so here we are checking, here we can check whether our pseudo-random numbers behave like independent copies. And goodness of fit tests, well, here we can check as in the empirical tests, whether the pseudo-random numbers we have or the methods which we are building on the pseudo-random numbers like Marsalla, Box-Mahler, reproduce the target distribution in a nice way. Okay, so here in red is a CAT test, we have done this, and here in red is a chi-square independence test, and here in red also we have the Kolmogorov-Smirnov test, while the test in red we have done or will do. Okay, and statistical testing, well, is sometimes a bit sometimes does a bit twiggles in the mind. Statistical tests for Monte Carlo is a bit easier. Well, why is it easier? Because we know that our pseudo-random numbers are fake. They are never realizations of uniformly distributed random variables on 0, 1. They are never realizations of standard normal distribution. So our test hypotheses are wrong, always wrong. They cannot be true by construction of our pseudo-random numbers. So here statistical tests is, well, testing the goodness of the fake. So the pseudo-random numbers are fake, and we are testing how good the fake is. So how good we can cheat on the tests. So this makes life here a bit simpler, because what we are doing with the testing is we are looking at how good our pseudo-random numbers or the assumed samples of the standard normal distribution are independent, are imitating the uniform distribution or the standard normal distribution. So we are always checking how good the cheat is. Okay, and let's start with the chi-square independence test. And the goal is to check whether the data x1, y1 up to xn, yn can be a realization of IID random variables x1, y1, xn, yn with pairwise independent components xi, yi. So we are checking this. So we have IID copies of x and y, and we want to check whether x and y are independent. And the idea is of the chi-square independence test is, while in all tests we have to fix the significance level in advance. While significance level is a notion which you will probably have seen by now, either in Introduction to Statistics, Stochastics 2, or Econometrics. So that's again a small alpha, which will appear later on. And the idea of the chi-square independence test is, well, to look at the empirical frequencies. So to look at the joint empirical frequencies of x and y, and to compare this with the empirical relative frequencies of the x and the y. Why? The joint frequencies and the marginal frequencies. Well, if we have independence, the product of the marginal frequencies should be the joint frequency. Okay, so we are looking at this, and we are rejecting independence. Well, if the data leads the value of our test statistic, which only would arise with a probability of less than alpha if the assumption of independence would be true. So this is how alpha comes into play. So we are looking at our test statistics, which is built with the empirical frequencies here. Then we are looking at values we would get if the assumption of independence would be true. And if we are getting with the small xi, yi's values of our test statistics which are not typical, we reject. Okay, let's get a bit more detailed. So what we have to do is to build a partition of R. So I1 up to Ik are Borel measurable, and they are building a partition of R, and J1 up to JL are also Borel measurable. They are building also a partition of R. And this here is used for the values of Y, and this is used for the values of X. Okay, and here we have now frequencies. So here we are counting. So Nij, Ni, and Nj are just random variables which count. So what do we count? So here we run through xd and yd from 1 to n. And we are checking whether xd and yd lies in the product of ii and jj. If yes, we get a 1. If not, we are getting a 0. So we are counting whether we fall into this interval here. Okay. Ni and nj, well, are only for x and y only. So here we are counting, looking only at the xd's, whether they lie in ii or not. And here, and for nj, well, we are only looking at the yd's, whether they fall into jj or not. So here we have the joint frequencies, and here we have some marginal frequencies. Okay, so that's the setup. So we are counting on how to build a test statistic from this. The test statistics, well, is done in this way, but first some further motivation. So if xi, yi up to xn, yn are really IID and have the property that xi and yi are independent, so that the joint distribution of xi and yi is just a product measure, then we get by the strong law of large number that Nij divided by n, while this converges almost surely to the same value as the product of these limits here. So that's the joint frequency, the joint relative frequencies, they're converging to the same values as the product of the marginal frequencies. So that should be for n large, and if you drop the limits, so these values should be close. And that motivates the test statistic here. So we have here Nij times n minus Ni times Nj. So if we have really independence, so we should get here a small value. And then we are standardizing by n times Ni times Nj. Why we're doing the standardization? Well, this helps to say something about the distribution of this random variable Qn. Well, a lot of statistical testing is having the appropriate limit theorems, and here for the chi-square independence test, one can use this the fact, or one can use the proof of this fact that Qn converges while under Fermat moment assumptions on x and y. So we need appropriate square integrability at least. So Qn converges for n going to infinity to a chi-square distribution. And with the number of degrees of freedom like this here, or as this here, k minus 1 times l minus 1. So our test statistics compares the relative joint frequencies with the relative marginal frequencies, standardizes it, runs over all partitions, and then if we have summed up this, we get the test statistic Qn, and Qn converges to a chi-square random variable with k minus 1, l minus 1 degrees of freedom. And this we can use now. So if you haven't seen what chi-square distribution is, or if you have forgotten it, if you have set 1 up to set r, IID standard normal, if you square it, sum it up, then you get a random variable which has a chi-square distribution with r degrees of freedom. Okay, and now we can build the following asymptotical test. So this is now our test. We are on the given level alpha. So our null hypothesis is that the joint distribution, well, is a product of the marginal distribution, which means our null hypothesis is the assumption of independence. And the alternative hypothesis is, well, we don't have independence. So the joint distribution is not the product of the marginal distribution. And the rule, our testing rule, is while we reject our null hypothesis if this quantity here has a value which doesn't fit to our null hypothesis. And what is a value which doesn't fit? Well, if this Qn here is greater than this thing here, and here we have the inverse distribution function of the chi-square distribution with k-1, L-1 degrees of freedom evaluated at 1 minus alpha. So we are rejecting our null hypothesis if we see values of this test statistics which would only appear under our null hypothesis with a probability less than alpha. Okay, and what are the small n, ij's, ni, and j's here? Well, nij, ni, and j are the quantities which one obtains by replacing in our random variables the random variables xi, yi through the realizations x1 up to xn, y1 up to yn. So this is our test. We are rejecting independence if this Qn has values larger than this expression here. Okay, and let's do another example. It's a toy example. So while random numbers which are standard normal or which appear to be standard normal are important, and here we are checking rand_n, so that's a built-in MATLAB generator, and I have generated here 10 to the power 4 realizations of rand_n. I paired it in pairs of xi and yi, so to check whether these two can be realizations of independent random variables, so that xi, the first component and second component, are independent. Okay, one needs to build a partition, and it's a toy example, so here I've taken the interval from -infinity to 1, -1 to 1, and 1 to infinity. Okay, then we have 10 to the power 4 realizations, and we can check in which intervals they fall. And if you does it, you get this value. So here runs j, here runs I. So, and as expected, well, the normal distribution is centered around 0, so the most realizations are in the center interval -1, 1 for both. And here we have the other values. Well, look nicely symmetric. And well, if you now compute Qn, so if you compare the relative frequencies of the joint distribution with the relative frequencies of the margin distributions, well, for the marginal distribution you have to sum up here, sum up here, sum up here, and here, here, here. And if you square standardize, etc., well, don't do it by hand, let's do it by computer, then you get this value of the test statistic here. So Qn is 4.5295, and well, if you're having the significance level 0 for 0.5, so the value we need to compare is this value. So we have here 3 intervals for both components. So k and l are 3, k-1 is 2, l-1 is 2, 2 times 2 is 4. So we have to look at the chi-square distribution and at the inverse distribution function, and now evaluate it at 0.95. And if one does this, one gets this value here, 9.4877, and 4.5295 is much smaller than this, so the null hypothesis is not rejected. So given these data, well, they don't give values of the test statistics which you can use to reject the claim that they are actually independent realizations, or pairwise independent realizations of standard normal random variables. Okay, that was the chi-square independence test, which we can use to check the quality of our pseudo-random numbers generators, or more precisely of the methods we have built on our pseudo-random number generators to generate samples from a target distribution. And now let's look at goodness of. Okay, so let's now look at goodness of fit tests. So the Kolmogorov-Smirnov test is one of the tests which does this. So here we need the assumption that our target distribution has a continuous distribution function, and well, assuming that the target distribution has a Lebesgue density F0, well, this is enough. Okay, so the goal is to check whether the samples we get from our method, whether these samples can be samples of the supposed target distribution. So we are checking whether the data x1 up to xn, which we get by our method, can be really realizations of IID random variables x1 up to xn with supposed target distribution function capital F0. So capital F0 is the distribution function corresponding to this Lebesgue density. Okay, and well, as almost always in statistical testing or asymptotical statistic testing, well, there's a limit theorem behind it, and here are two limit theorems behind it. So the first thing is, so if x1 up to xn are IID with distribution function f0, then by the Glivenko-Cantelli theorem, this thing here converges to 0. So what we are comparing, f0 of t, that's a supposed distribution function, and here we are summing up the realizations, and we plug in the realizations in the indicator function of the interval minus infinity t. So if xi has a value less than t, we have a 1, otherwise we have a 0. In other words, well, this is the empirical distribution function. And the empirical distribution function we are comparing with the real distribution function, and then we take the absolute value and then the sup. And Glivenko-Cantelli tells us if x1 up to xn are IID with this distribution function, then this thing here converges almost surely to 0. Okay, and as I said, this is the empirical distribution function, f and t, which we can abbreviate with f and t. So that's the expression we had. And the bit of rewriting gives that we are just counting how many xi's are less or equal than t, and then we standardize this with 1 over n. So f and t is the empirical distribution function. And the Kolmogorov-Smirnov test compares the empirical distribution function with the supposed real distribution function. Okay, and we have this almost sure convergence. If x1 up to xn are really IID with distribution function f0, for testing this is not enough. We need also a certain limit theorem for the distribution. And here we have the following fact, which goes back to Kolmogorov and Smirnov. And so if x1 up to xn are IID with distribution function f0, if we compare the empirical distribution function and the supposed real and the distribution function, absolute value sup, and then blow it up by square root of n, and this converges in distribution to another random variable, and this random variable has the so-called Kolmogorov distribution function. The Kolmogorov distribution function, or Kolmogorov distribution. So what does the Kolmogorov distribution look like? Well, it has this distribution function here, so it lives on 0 infinity. Well, this is rather obvious because this is positive. And well, the Kolmogorov distribution function is given by this infinite sum here. So k runs from minus infinity to infinity, 1 minus k, so it's alternating, and then we have e to the power minus 2 to k squared x squared. Okay, that's one way to write down the Kolmogorov distribution function, and this thing is really important. So there are several other expressions. So one of the other expressions is here, which you get by manipulating this b infinite series. So this is the distribution function of the Kolmogorov distribution. Okay, so and now we have all we need. So then on this we can build an asymptotical test, again on the fixed level alpha. So the null hypothesis is that the f of x, or the distribution function, is f0, and the alternative hypothesis is that, well, f of x is not equal to f0. And well, how do we do this? How do we test this? So we reject the null hypothesis if square root of n times dn, which is the square root of n times the empirical distribution function evaluated for our data compared with the target distribution function. Well, and then again, absolute value and the soup. If square root of n times dn takes a value larger than the inward distribution function of the Kolmogorov distribution evaluated at 1 minus alpha. Okay, so what we have to do is we have to compute this expression here, and this is a bit cumbersome. Well, because the empirical distribution function is discontinuous, it only changes at jump points. But what helps a bit, so that the primum here is attained at the jump points, because we have piecewise constant functions. So it's attained at the jump points x1 up to xn, while of the empirical distribution function for the realizations. So as always, realizations small letters, random variables capital letters. Okay, and so since the supremum is attained at the jump points, we can rewrite dn in a bit different way. So dn is given as the maximum over the i's, and now the maximum of the absolute value of fn xi minus f0 xi and fn xi minus f0 xi. What is fn xi minus? Well, it's the left limit here. So we need to look at fn xi, and we need to look at the limit from the left, and to have to compare this with f0 xi, absolute value, max, and then we get our value for dn. Okay, so let's finish today's lecture with a small example for the Kolmogorov-Smirnov test, and here for normal deviates. So here we are checking whether the numbers we are getting for our methods to sample from the standard normal distributions are okay, or at least pass these tests. Okay, and here we have the four methods we had: rand_n, norm_inf, plus rand, so MATLAB built-in. rand_n is the cigarette method, Boxmala and Masalia. And for all I created 10 to the power 6 samples. Alpha is chosen 0.05, and here this quantity where we need to decide whether we reject or not. Well, it's the inverse distribution function of the Kolmogorov distribution evaluated at 1 minus alpha, and here divided by square root of n. Why divided by square root of n? Well, the real test statistic is square root of n times dn, but if you use dn, you have to divide here by square root of n. And this is 0.0014. Okay, and if we look at the values of dn, in all the cases, they are smaller than this critical value here. They are always approximately of the order 10 to the power minus 3. And so in all cases, the null hypothesis is not rejected. So based on the Kolmogorov-Smirnov test, we cannot reject the assumption or the hypothesis that the numbers we are getting here in this sample are realizations of IID, standard normal distributed random variables. Okay, there's another quantity I added here, the so-called p-value, and you see the p-value is always larger than alpha. Here also approximately 10 times, 5 times, 4 to 5 times, here 2 times. And the p-value is the largest alpha for which, for the given data, the null hypothesis is not rejected. The larger alpha is, the more skeptical you are, the more even realistic data you exclude under the null hypothesis. So this is, for practitioners, this is a measure, well, how good the data really is. Okay, So in all the cases, well, we cannot say anything about against. We cannot say anything against our generators. So at least they pass this test. And I didn't implement it by hand, so in MATLAB there's a built-in routine KS test. Okay, that's all for today. Thank you very much.